So overall, I try to analyze the maturity of what Australia has, of course, based on what the world has, and to identify possible gaps and opportunities in this interaction between policies and legislation. So in here, when I say policy, just so I don't have to say policy and legislation, policy, I'm talking more in a lato sensus. So which encompasses the legislation and encompasses the governmental structure, all of that. Okay, so basically, my question is developed through 5 splits. So first one is that Australia recently reawakened its space sector. So with the Australian Space Agency, for example, or enacting new space policies, new space legislation as well, and is also increasingly considering space as a relevant domain for all sectors of society. So of course for defense, but also for industry, for the civil, for everything. In this context, ESPI, the European Space Policy Institute, already recognized that while direct ASAT attacks, for example, they are very unlikely due to the cloud of debris and the international shaming that would create, cyber attacks would present as the most probable source of a space attack. And this is particularly worse for Australia because according with the latest ACSC reports, Australia is suffering an increasing number of cyber attacks, and these attacks are also increasingly complex. So how do we mitigate this? So of course we have the technical side with most people are looking at, but this problem can also be mitigated through a coherent and solid legal and policy framework. So this leads to my question. So what I assess on this research is how does Australia's policy and legal framework contribute to the cybersecurity of its space infrastructure? So some bases here, we all know this, we read this pretty much every day. Space is increasingly congested, contested, and competitive. So it's an environment that is increasingly all of that. So we know that uh, so by contested, due to the rising number of space objects in orbit, is contested due to the growing threat of adversaries, and competitive because we have more people, more industries, a greater number of states and non-state actors accessing space. But the thing is, the problem is not being congested, contested, and competitive. Because to be honest, so is FIFA's World Cup is increasingly congested, contested, and competitive, and it's becoming harder for Brazil to win, unfortunately. So, what is the real problem of being congested, contested, and competitive? The real problem is due to the lack of a clear regulatory framework agree upon, if not everyone, because everyone would be very hard to agree upon anything, but at least agree upon most space relevant states. So here I'm talking about the United States, China, Russia, and all the growing powers as well, like India, Australia, Brazil. And arising from this, so this is speaking from a broader regulation of space. So arising from this, the intersection between cyber and space is less developed than space itself. Okay, but so my research, that's what I try to find. So this particular intersection of regulation between cyber and space. So I'm trying to see, okay, where are you? How are you being developed? What are the major influences that you suffer from international frameworks as well? And how do you interact within Australia? Okay, and why do I think that this is important to investigate, is relevant? So why cyber attacks are relevant to analyzing this new space framework? So the new space framework, we all know what it is. So I'll already jump into the reasons. So due to cheaper technologies like COTS, for example, the bar to access space is lower. So this is creating more pressure in already congested orbits, LEO, MEO, GEO, whatever. Okay. In addition, as I already mentioned, an SAT attack would cause collateral damage equally shared by everyone. So this is not a very probable source of an attack. We already had demonstrations of power of okay, look what I have. I have the technology to send ASAT attacks in space, but most of policy developers, most of social scientists that study this this topic already considered that this is way more than a demonstration. It's just a demonstration of power, not a weapon that will be used in normal conditions. And cyber attacks, they offer a cheaper, a harder to trace, less technically demanding uh, counter space capability, so that can be available to a greater number of actors, state and non-state actors. And the cherry of the top is that cyber attacks on space are in a policy and legal gray zone. So they are not very regulated. Space in a manner is not very regulated. So we can notice that space, we have a huge gap here. So since 1979, we don't have any binding legislation. So space law is a part of a bigger branch, which is international public law, and we have soft law and hard law. So hard law are binding legislation. So like the Outer Space Treaty, for example, the Rescue Agreement, all of that, and they can be preferable to enforce power into a domain as a space. But since 1979, we don't have anything. So this means that as the environment gets more complex, the legislation are more scarce. And even considering the five international binding treaties that we have, the last one was a complete fiasco. Only 18 states agree with it. None of them are powerful space state. So we have a huge gap in this, and nowadays we pretty much gave up of binding treaties, and we changed the approach to soft law instead. So from hard to soft, now I hear that this title is a little bit inappropriate, but we are changing the direction to a soft law approach, because mainly because the hard law approach was created for three specific goals. The first one was the peace that we needed in the race, in the space race between the United States and the Soviet Union, and we already achieved that. Once we achieved that, we had more countries being able to develop space technologies, so the environment became more complex. We didn't need to just satisfy the needs of only two countries anymore. So now we have four, five, six, seven priorities that would be taken into account. So it became harder to create a consensus and in this sense. And also after 79, during the 80s and the 90s, space as a priority for most countries saw a decrease, including Australia. So at the moment, my research is assessing this international framework to see if I can find something appealing to my topic. So in the Australian domestic framework, I already assess the international partnerships that it has and how it can affect the theme. So the main defense partnerships, military or strategic or whatever you want to call. So AUKUS does not have a specific focus on space. ANZUS recently 2011, but like recently extended the partnership to aggressions in cyberspace, but nothing was developed from there. The Quad has two different working groups, which could be great. So it has a cyber working group and a space working group, but they don't work together. So there is no intersection in there. They develop different documents for different goals in this. The Five Eyes from 2019 and 2022 did not provide any agenda regarding cybersecurity of space. The combined space operations Although it considers a threat, the cyber attacks on space, it also did not develop anything on that, and neither Artemis is not the focus of the Artemis Accords. So overall, it's noted a lack of specific policies regarding the cybersecurity of space. So okay, how about the domestic documents of Australia, the domestic policies and domestic laws? So already I'm revising the governmental structure. So the theme is dispersed between different governmental branches. We don't have a specific branch that deals with the cybersecurity of the space acts. So of course there is a focus on the Department of Defense, but we also have smaller governmental structures in Home Affairs, Foreign Affairs and Trade, National Cybercrime Working Group, in all of this. And then I started to assess the domestic legislations and domestic policies. So to do this, I did a qualitative data investigation through a documental analysis. So I started with a lot of documents, a lot of them, and then I created 5 explicit criteria in which I would only analyze documents that were Australian made for Australian use, developed by Australian governmental entities, publicly available, released not before 2016, especially because then it could encompass the defense white papers of 2016, and that was entirely or at least partially dedicated to the intersection between space and cybersecurity. As an extra step there, I did a series of I did 2 stakeholders workshop with the assistance of SmartSat. So this SmartSat project, I was able to talk about with important space stakeholders from Nova, Airbus, from SP, or the Australian Space Policy Institute as well. And I divided between 2 workshops. So the first one was more focused on IT people, engineering, physics, people who I don't really understand, to be honest. But so this was the first one. The second one was a cooler one, in my opinion. So my people, lawyers, policymakers, all of that, just really cool people. So on the second one, I was able also to mediate, so I could directly ask participants, okay, in this case, do you see the applicability of any particular policy, of any particular legislation? So then from the list that I already had, I could cross some documents that were not interesting as I thought it was, and to add some that I had already discarded, and people started to point out they were really valid to be inserted in the research. So through this 3 data selection process, I was able to, at the moment, I have those, I'm assessing those documents here. So I divided into implementation documents, strategic documents, and the Australian domestic legislation. So of course, I note that this list tends to grow even more as new documents are developed. And they are being developed, which is a nightmare. Every time I open LinkedIn, I'm like, oh, more documents, but that's life. That's the PhD life. After doing this, I also propose a structure focus method to how how I am assess this data. So it's a structure because it asks the same pre-established questions to all of the documents. So this method could be replicable. And sorry, and it is focused because it's not in all documents in the Word, and it's just on these ones here that I already explained the criteria. So the questions are: what is the contribution of the document? What is the gap of the document? So these 2 questions can allow me to examine both what the document brings and what it doesn't bring, so what is lacking over there. Third question is: how does this document interact with the remaining Australia policy framework? So then I can do a more systemic analysis, because it's not only if this document does not talk about a specific topic, it doesn't necessarily means that there is a gap there, because this can be talked about a different document. And number 4 is if this document is in line with has been developed internationally. So then I can assess the international framework as well, and do comparisons between the Australian domestic framework and the international one. So my findings, keep in mind that I'm just starting my second year, my 14th month of PhD. So until the moment, my findings are regarding the strategic documents, that some of them are way more focused in space specifically, and other more focused on the cyber. The space ones, they always consider cyber as a relevant threat, but the cyber ones, they are not they are not made, they don't consider a space, they are created by a broader audience in that sense. So Australia has now an interest to become a really cyber secure nation, but the policies they are developing are more for a broader audience, not for specific ones. The sorry, let me just go back here. The findings on the implementation documents is pretty much the same as the strategical cyber one, so they are catered to a more broader audience. In the absence of specific space cyber toolkit, some of the general toolkits, they can still be applied to the space sector, uh, mainly in terms of personal security, in terms of the structure security, but nothing very detailed. And some of the implementation documents, they are also a requirement for more specific governmental plans, for governmental programs, such as DISP, the Defense Industry Security Program membership. So in a nutshell, so far, what I found is that Australia still does not have a specific policy specifically dedicated to the cybersecurity of the space infrastructure. The topic is also scantily addressed overseas. So internationally, we also don't have like this is the Bible to this topic. We don't have this yet. I also found that the cybersecurity strategy, which is a requirement imposed under the Space Launches and Return Act of 2018, is balanced to a degree in two implementation documents that I assessed, but neither of them they are catered for the space environment. So there is a gap in this sense. So the same legislation, for example, it brings as a requirement debris mitigation strategy. So this one, it is catered in internationally recognized guidelines. So it is specifically catered for that. The cybersecurity one, unfortunately, it isn't. And the topic is neither protected by any binding international space legislation. So there is a huge gap in this. And finally, this is my bibliography. And thank you for listening. Any questions?
Venicus, thank you for that presentation. Really interesting area that you're covering. I will encourage and remind colleagues, if they've got questions, please put those into the chat. I see one coming up there, but so Venicus, I don't know whether you've got your chat open, but just in case and for others, I'll read it out. A question from Brandon. What is it that makes space cybersecurity different than ground-based or normal cybersecurity? You got a response to that?
So yeah, two things. So first, the jurisdiction. So it's more legal, blah blah blah, in that sense. But the jurisdiction is extremely different in this sense, because the Outer Space Treaty did not treat jurisdiction as we treat nowadays. So first, it becomes in a gray area. So a normal cyber attack is already complex to assess jurisdiction, because cyber attacks can pass through several states between its end goal. And on space, it becomes even more complex, because you have another thing on top of that. And second, also the technical environment on space. The ground segment can be a space, cyber attack on space can be considered, especially by the Security of Critical Infrastructure 2018 Act and its amendments. The most recent was last year. But it's, yeah, there is these two differences there.
You're muted, Andrew.
Sorry, you muted.
Thank you. Our resident defence expert, Peter Kerr, has given you another reference to have a look at there in the chat. But Vinicus, I wanted to ask you, the role of science-informed policy development is very important across all disciplines. And I think it was about slide 13 or 15, you listed a whole lot of departments that had some level of responsibility in creating policy and laws in this area. I wanted to ask you, who do you think is the most influential, and who would you want to read your PhD and act upon it?
That's a great question. I think at the moment the most influential would be the Defense Department, for sure. The whole space sector is being pushed in a sense by the Defense Department. But like I said, there is smaller governmental branches along different other departments that are extremely relevant. You know, the theme is extremely dispersed, so it's difficult to point one as the Home Affairs Department is the main one by 90%. This is very hard, you know. Maybe I think the Defense Department pushes a little bit, but not a lot, you know. So probably the bigger two would be the Defense Department and the Home Affairs, but the International Affairs and Trade, for example, they did a beautiful job in the Australia International Cybersecurity development there, and how international law applies to the cybersecurity domain. So yeah, it's very dispersed in this sense.
Okay, well, I'd encourage you to try and figure out how you can get them to read the outcomes of your PhD, because I'm sure they'll all enjoy the read and be all very relevant to them. Vinicus, look, thank you for your time. I don't see any more questions in there, so we'll move on to our next presenter. Thank you very much.
And just I just see the comment that I not mentioned the SOCI Act. So the Security of Critical Infrastructure Act is a part of my research, and it's on the documents that I am assessing, and it's one of my findings that the security of this topic is usually under a broader spectrum of critical infrastructure, not space per se, under the SOCI Act. But thank you everyone.
Thank you. Okay. Thanks, Vinicus. We'll take back, and I'll introduce Jordan. Jordan completed his undergraduate degree with with Queensland University of Technology in 2021, majoring in mechatronics and computer science. During his final undergraduate year, he spent some time working with BAE in Cairns, sounds like a good spot, while conducting research relating to neural architecture search in partnership with Sentinel Vision Systems. Clearly that sparked an interest, and Jordan decided to pursue that area in artificial intelligence, and undertaking a PhD with a signal processing, artificial intelligence and vision technologies lab at QUT. Jordan, thank you very much for your time today. We're very much looking forward to your project presentation on subnets for scalable onboard AI in space.
Awesome. Thank you, Andrew. I assume everyone can hear me good and see the slides.
Yeah, look
awesome.
good.
So hi everyone. My name's Jordan Shippard, and my presentation will be on my PhD topic of efficient subnets for scalable onboard AI in space. So for this presentation, I'll first just introduce myself a little bit more, pretty much what Andrew said already, but then I'll go into the problem which I'm trying to solve, as well as a brief summary of the project, and then go over my completed and in progress work so far, and then just wrap up with some lessons that I've learned along the way. So a bit more about me first. As Andrew just covered, did my Bachelor of IT and Engineering at QUT, majored in Computer Science Mechatronics, did my undergraduate engineering thesis on neural architecture search, which was my first introduction into AI and deep learning. Then I'm currently a second year PhD student at QUT in the Signal Processing, Artificial Intelligence and Vision Technologies research group. And bit more about me personally. I've always loved video games and programming growing up, and I really developed my interest in AI from actually making video games throughout high school. It was from programming the bad guys, essentially, and the various non-playable characters. It was a lot harder than I expected and got me really interested in just what is intelligence from that. And then throughout my undergraduate degree, I fell in love with engineering and science, which ultimately led to pursuing this PhD research. So what is the problem then that I'm trying to address? As I'm sure many people here are already aware, there are many great applications of AI combined with imagery data from Earth observation platforms. But just some quick examples to highlight include natural disaster response, such as predicting flooded buildings and roads, as well as predicting and tracking wildfires. And there are many other environmental and ecological applications, such as tracking land use changes over time and agricultural applications, such as crop mapping and segmentation. Where the main point here is that there are many great applications of AI with the data from Earth observation platforms. And obviously, we want to be able to realize all of these applications. However, one significant problem is the cost of the Earth observation satellite. And ideally, we want as much coverage of the Earth for as little cost per square kilometer as possible. So this constraint has caused the industry to shift away from the use of the single large satellite and instead towards the use of a constellation of nanosatellites. And this shift fundamentally changes the nature of how we develop and train our AI applications so that we can use this data that the nanosatellites are capturing. So essentially, we want to learn from the observed data of a nanosatellite constellation to perform some downstream machine learning task. And there are two main approaches that we could take to solve this problem. The first being the traditional centralized learning approach, where you transmit all of your data from the nanosatellites to a single centralized location. And then once you have all that data collected, you can then train an AI model to perform whatever the required downstream task is. And the main downside to this approach, however, is you have that requirement to transmit all of the data, which takes a lot of time, and it introduces a significant lag between when you can observe data and when you're actually able to act on that observed data. We want to be able to remove this lag time by instead learning the task on board the nanosatellite, which does introduce its own set of challenges that need to be addressed, such as limited onboard compute and whatnot. However, it does also fundamentally change the learning setup, because now we have each nanosatellite observing its own local set of data, and it's not able to share that data with other nanosatellites. So we need a method of knowledge sharing. Well, it turns out that when this sort of problem formulation already exists as federated learning in the machine learning like broader category. So just briefly, federated learning was actually first proposed for the medical domain, where you have, say, hospitals which all have data on detecting cancers in detecting cancer in patients, and you would love to be able to train an AI model across all of that data. However, the privacy laws around the patient's data means that you can't collect all that together. So instead, what you could do is you could go around to each individual hospital and train a single model on that local data set, and then try to combine the knowledge from all of those locally trained models. And that way you're able to get the advantage of the learning, but you're able to also preserve the privacy of the users. And this is the same situation as ours, where instead of hospitals, we have nanosatellites, and therefore fits pretty well for us to use federated learning. Aside from this, what is the downstream task that we're actually training the model for? So, so far I've mainly been looking at image classification. However, we've sort of recently expanded this to this generalized category discovery problem, which I'll just cover a bit later on. So this here is just a high-level diagram that I created for the SmartSat conference last year, actually, just to provide kind of like a high-level overview of how the final solution may look. So in this, we've split this into 3 separate stages. The first is a ground training stage, where we want to be able to learn as much as possible from pre-existing Earth observation data in order to limit the amount of learning that we then need to be doing on board the nanosatellites. We'll then have the deployment stage, where we extract different subnets optimized for different hardware on the nanosatellites. And then these subnets will continue to learn from the data that the nanosatellites observe. And then we've got the knowledge transfer stage, where they just need to be able to communicate and share the knowledge they've learned. Our research goals for this project are to enable the effective and practical use of AI models on board nanosatellites in a constellation, and to solve general challenges in federated learning, which limit the learning potential on realistic data distributions. These are my supervisors for the project. So from QT, I have Professor Clinton Fuchs, Dr. Ken Nguyen Phan, and Associate Professor Arnold Willem, who is also associated with our industry sponsor, Sentient Vision Systems. And from La Trobe University, I have Professor Wei Zhang. So what is the current work to date then? So at the start of the project, we focus on that first stage of training the initial subnets and then deploying them to the nanosatellites. And from conducting the literature review, we came across this once-for-all method, which shares the same problem formulation as ours. So in this method, the authors train a single network, which is known as this once-for-all network, which can be scaled along various dimensions. And this scaling property then allows for the direct extraction of multiple subnets, which don't require any further retraining. You can just deploy them onto the target devices. And in order to achieve this property, as I mentioned, the network can be scaled along 4 different dimensions. So that's it can be scaled according to its width, which is the number of channels that it has, the kernel size, and the number of layers, and also the input resolution is the final dimension. The authors found that when training this network, the smaller networks in the population interfered with the larger networks. And so they proposed this progressive shrinking training in order to limit this interference. However, when we were looking at implementing this method, we found that this interference wasn't actually as bad as the authors had initially thought. And we found that we could overcome the interference with properly training the subnets in a random sampling method. So this then became our first published work, which was accepted to the Computer Vision and Pattern Recognition Embedded Vision workshop last year. And these here are just a quick snapshot of some of our results. Our methods here are in the green and orange, and we show that we can just train a better performing subnet population in much less time than the original method. And then during this work, we also realized that this deployment stage isn't actually where the main challenges of our problem lie, and that it's in the knowledge transfer and the onboard learning stages of federated learning. So we began to look much more at those next. And in federated learning, there's this core problem of local drift, which occurs when clients train on uneven data distributions. So I'll just give a bit more of an intuitive example here to help explain it. So this is the ideal case where we've got our clients on the x-axis and they all have the same number of examples per class. So in this instance, we've got our centralized data set. We then split that up so the distributions are even. Just pretend this is like a model that's classifying cats and dogs. And then as the two local models train towards their two local minimas, because the distributions are even, the combination of those models is still aligned with the global minima. However, when our data is more realistic in this non-IID case, so it's more uneven, some clients have more examples of some classes than others, and they might have no examples of some classes. And this is just a more extreme version. So what occurs here is that as the models train towards their local minima, the combination of these models is no longer aligned with the global minima, and that misalignment results in worse performance, and it's also that's what's referred to as the local drift. So when we began approaching this problem, it was around the same time as the generative image models were starting to become popular. So when looking at it, we were wondering if perhaps we could generate synthetic data to correct these local training distributions. So these here are just some quick examples showing how we can create a number of high quality synthetic variations from a single real image on the left. However, when we sort of looked at this a bit more around in our federated learning problem, it didn't, we realized we couldn't really use it because it would require us to generate from a real image, which would require some level of data sharing. But at the same time, we also came across the more fundamentally unanswered question of, can you use these synthetic images to train? And also, is there a way to remove the real image so that you can generate just synthetic data sets and potentially remove the need for data collection at all? So we found that you can do this, and this then became our second published work, which was accepted into the Computer Vision and Pattern Recognition Generative Models for Computer Vision workshop this year. And in this, we just demonstrate that we're able to generate fully synthetic training data sets, which can be used to train any downstream model to classify real images. These here are just some more synthetic images examples along the bottom row, with the real image examples from the data set, from the real data set along the top row. And this is just a quick snapshot of our results, mainly just showing that we're able to classify the real images, and we're also able to improve the quality of our synthetic data sets for training. So at the conclusion of this work, we then started to think a little bit deeper about what is the desired downstream task that we want to demonstrate our federated learning system is then capable of. And that's where we came across this generalized category discovery, which fits well. So I'll just explain it quickly here. So in generalized category discovery, you have your AI model. It's given these images in green and the labels. So it's given, say, examples of frogs, elephants, and birds. And then it's trained on those images so that when it's presented with a new set of images, so all the images with question marks, it can then correctly classify the images it's previously seen. So it should be able to classify all the frogs, elephants, and birds, but it should also be able to group sets of unknowns in the new data coming in. So it should be able to group the images of tigers together and say this is an unknown set, but this is clearly the same thing, and it should be able to do the same for the cats, should be able to group them. So in our approach, however, we want to take advantage of some of the recent advancements in vision language models and to remove the requirement for the initial labeled examples. So instead, we just want to be able to simply describe in natural language the classes that the model needs to look for, and then just have it solve the problem from there. And we currently have a baseline of this working, and we're working on improving it at the moment. So I'll just go through that quickly. In our current approach, we have, say, our images on the top here, which is what we wish to classify, and we have our prompts, which describe the things that we want the model to look for on the bottom. We can then embed the images using the Dino V2 model, which is a model trained by Meta, and it gives us a set of image features, which we can then just visualize on a TS&E plot here, where the different colors and clusters are the same image categories. We can also then embed our known prompts as text features by first embedding them into the clip feature space and then projecting them into the dyno feature space using a trained projection head. And then with these features in the same feature space now, we can then find which cluster belongs to which class by using the cosine similarity. So in this one, we would say looking for which cluster is the airplane by asking it to find, by asking the similarity of an image of an airplane and not an image of an airplane. And then using the image and text features in this way, we can then use k-means clustering on the image features with the center initializations from the text features to figure out our known and unknown sets of points. And next, we just need to be able to differentiate the unknowns here. So say the green set, if that's the unknowns, we just need to figure out the clusters within that. So these are a snapshot of our results so far compared against other methods. The main method that we're comparing against here is the Fed GCD method, which is just another federated generalized category discovery method. And the values of alpha indicate the levels of data heterogeneity in the local training data sets. And so far, these results are fairly promising considering our method can only detect the known classes from the prompts, and we should be able to get a further accuracy improvement when we're able to detect and separate the unknowns, which is what we're currently working on. So just to wrap up now, some of the lessons I've learned so far. The first one is that sometimes defining the problem is as hard as solving the problem, and I've found that it's always better to spend more time fully thinking through and formulating the problem, just because it helps with clarity as you're working on things and gives you better direction. The next is that doing too much of a literature review is better than doing too little, because I've found there's nothing worse than just working on a problem for a long time, then finding a paper which directly addresses your current problem, and you just didn't find it earlier because you were rushing the literature review to get into solving the problem. And then lastly, the most important, I think, is to find problems which are genuinely interesting to yourself. That way, you're always just more motivated to work on them and to just do a good job. So that concludes my presentation. Thank you all for listening, and happy to answer any questions.
Lovely. Jordan, thanks for that really interesting presentation. The team and I attended an AI breakfast seminar this morning, and I'm sure I saw that cat that you had on one of your slides on one of theirs. So it must be the right cat for the right AI presentation.
Yeah.
Wondering whether there are any colleagues, just a reminder to pop those questions into the chat. Jordan, I was, perhaps while that's happening, I was interested in how you found the relationship with the industry partner and their support for your project in giving direction, whether they're looking at particular outcomes from you or guiding you around this for their business purposes. Just interested in your experience with that.
Oh, it's working with the industry sponsors been great. So that I started working with the industry sponsor in my undergraduate project, and then they were able to stay on through. And that Arnold's support, he's the main one from industry that I've been working on. He's been the main help so far. He has a lot of academic experience and industry experience, so he's been really good at managing those like two sides of it, so that he, as someone from Sentient, from the industry, he can get outcomes which are interesting to him and his company, but also are still interesting like academically as we're pursuing papers and whatnot. And he's just given me a lot of freedom to sort of explore whichever area I kind of want to look at, even if we have to look for a bit of the connection to the core project at sometimes. But it's been, yeah, so I'm super grateful for the support from industry for that.
Yeah, that's great. Looks like Jason in the chat wants to catch up with you out of session. But I was also interested in whether you're finding in terms of the image matching, whether there's any substantial differences between when you're trying to identify those images and that manipulation of the data that you had for different types. You talked about trying to identify aeroplanes, but do you see a level of consistency regardless of the images that you're looking at, or are there more challenging things as part of the imagery analysis? Maybe when there's, it's just a green field versus a city where there's more distinguishing features.
Yeah, the hardest bit sometimes is that a lot of the methods that work really well are focused on kind of general like data. So like looking at, classes of like different animals or like very different domains, versus when you look at a lot of satellite data, it's a lot harder to distinguish, say, some of the classes that are present. So there's definitely an extra step of care that you have to take. You when you look at a method that previously might perform really well, it might not be might not just carry perfectly over to the satellite domain, just because the data is a lot more fine-grained than what a lot of the other core problems like sort of focus on. So that's really the key thing to be cognizant of as I'm working on everything.
No worries, great.
Awesome.
We don't have any further questions in the chat. Let me say thank you, Jordan. Great presentation, really interesting. Very much looking forward to the latter parts of this, and I'm sure we'll hear more from you later on.
Awesome, thank you very much.
Lovely. Okay, so moving forward now with our third presenter, I'd like to welcome Wakomba to give her presentation. Wakomba is a PhD student with the University of South Australia, working as part of Jill Slay's team there in the areas of cybersecurity. Wakomba's PhD focuses on space systems cybersecurity, with a particular focus on the integration of SDN and space systems. Wakomba is also a lecturer with, I still believe, the Namibia University of Science and Technology. And I think, Wakomba, that was part of your undergraduate program, or perhaps a master's program previously.
Yeah,
so,
yeah, that's correct.
Lovely. Wakomba, thank you very much for your time today. Very much looking forward to your presentation.
Thank you, Andrew. Good afternoon. My name is Wakomba Ohongora, and I'm a PhD student at the University of South Australia. My principal supervisor is Professor Jill Slay, and my co-supervisors are Dr. Yue Cai, Dr. Ronald Mulinde, Dr. Mamelo Tignane, Dr. David Omrod, and my industrial supervisor is Shane Burnett from Southern Launch. For this presentation, I'll begin by discussing the motivation for my research and the research gap that I have identified. Then I'll discuss the integration of software-defined networking in space systems. And lastly, I will look at the methodology and the progress and method and the accomplishments that I have made so far. So as we all know, space systems are vulnerable to cyber attacks, and they represent a single point of failure for the various industries that rely on their availability and their integrity. The space system architecture is limited in terms of manual configuration and control of the space system. So this results in scalability challenges. And so the integration of software-defined networking in space system can provide automation, a centralized view, and also control of the entire space system. So software-defined networking can provide ease of deploying security policies within a space system. So this can help the network managers and mission operators to easily deploy any security policies and have a centralized view and configuration of the network. But even though software-defined networking offers all of these exceptional features for space system, it is still vulnerable mainly at its controller point. So because the control point is the single point of configuration, so it is the most attractive to attackers when it comes to compromising the SDN architecture. So therefore, there is a requirement for intelligent security controls to secure an SDN-based space system. So by reviewing literature, I identified a research gap, which is the scope of my PhD research. There's work that has been done in software-defined networking, cyber threats, and there's also work that has looked at cyber threats in space systems, but there's little literature that has looked at software-defined networking integration in space system. So that is the scope of my research project. And my research aims to address three major knowledge gaps, which is securing a space system and integrating software-defined networking and space system, and then implementing an intelligent security control for SDN-based space systems. So the intelligent security controls are essentially security measures that will use machine learning or deep learning to analyze the data and make decisions based on that analysis. So this can be prevention or detection systems that will be implemented in the SDN-based space system. So ultimately, my research is looking at countering potential security threats against SDN-based space systems. So before I discuss the integration of software-defined networking in space, I will just do a rundown or overview of software-defined networking. So basically, SDN means replacing traditional hardware components with software. So this is an approach that separates the control plane from the data plane. And in this figure 2 here, it shows the software-defined networking architecture, and it consists of 3 planes: the data plane, the control plane, and the management plane. So the management plane, or the application plane, it consists of different applications that are required for the functionality of the network. So for example, security policies or network configuration applications. Now, the control plane, it acts as the strategic control point in the SDN network. So it manages the parts of the packets within the network and also provides a high-level abstract of the entire network. The data plane, which is also known as the infrastructure plane, it performs data forwarding of network packets, so based on the instruction that it has received from the controller. So software-defined networking, it transforms the traditional networking architecture. So with the traditional networking architecture, the control plane and the data plane are combined. And so this results in a complex network management and also in difficulty in scalability of the network. So the separation of the data plane and the control plane, it simplifies the management of the network, and it enhances the ease of deploying new software and applications in a network. So the space systems can leverage this software-defined networking capabilities. So what this will look like where SDN is integrated in space systems is, for example, placing the SDN controller on one of the satellites. So I'm still doing literature review to determine the most visible position to place the SDN controller and to place the other 2 plane, the infrastructure plane and the application plane. So this diagram here, figure 3, just shows an example of how an SDN controller can be integrated in a space system. Now, an example is placing the controller on, on the ground segment. So security issues in software-defined networking-based space systems. So all 3 planes of SDN are vulnerable to cyber attacks. But according to research that has been conducted, the control plane is the most vulnerable to attackers because it is the point of configuration for the entire network. And so it can be a single point of failure during an attack. So one of the most persistent attacks against SDN is the distributed denial of service attack. So the attacker overwhelms the controller with fake traffic, which results in network failure, and so it compromises the rest of the network. So another security issue, for example, could be a physical attack where an attacker can gain unauthorized access to a ground station to disable it or to take control of a mission or the satellites. So my research aims to develop intelligent security controls for SDN-based space systems. And to achieve this, I'm currently performing a security analysis of threats against space systems and an SDN. So I've been looking at the MITRE attack framework and the SPARTA framework to identify any threats and tactics that are used by attackers against space systems and software-defined networking. Secondly, the next step will be to simulate a network where SDN is integrated in a space system communication network. So for that, I plan to use the MiniNet simulation tool. Lastly, I plan to develop an intelligent security control specifically for SDN-based space systems. So this will either be a machine learning or deep learning-based security control that will be placed on the controller and then simulate the cyber attacks that I will have identified in the first step of the methodology within the SDN-based space systems. So in this step also, I will be testing and evaluating the machine learning or deep learning-based intrusion detection or prevention system. To conclude this presentation, I'd just like to highlight some of my achievements and the progress that I have made so far. So this is the 13th month of my PhD, and so my confirmation of candidature was in February, and I did a poster presentation at SciSec conference that took place earlier this year, and I published a paper at the ECCWS conference earlier this year, and I was awarded Best PhD Paper at the conference. And I presented at the Australasian Satellite Forum, so I just presented a little bit of my PhD work. And I have an abstract accepted for the Ascend conference that will be taking place in October. And so all these publications fit into my final thesis, or they are aligned with the objectives of my research. So for the rest of the year in my year 2 of my PhD studies, the next step would then to start with the SDN simulation in MiniNet. So I'll be simulating the SDN architecture integrated in space systems before I begin with developing and placing the machine learning or deep learning control onto the controller to identify or to prevent attacks from this network. So like I said, I will then also do the cyber attack simulations in the MiniNet, and I plan to publish another paper in my second year, and then also as part of that, developing the machine learning, deep learning based security control, and all of that will be also, in the meantime, I'll be working on thesis writing as I test my work and do implementations and my results. I will be busy with thesis writing. And in the end, I'll be evaluating or comparing my machine learning or deep learning based security control with other models that have already been implemented, just to evaluate my security control. And I plan to do a 4th publication and have a thesis write-up, and then have a PhD defense presentation at the end of my year 3. Thank you very much for your attention. I welcome any questions that you might have.
Well, Konstantinos, thank you very much for the presentation. Really interesting area that you're working on. And I echo actually Alison's comment. Congratulations on your Best Paper Award. We must recognise and capture these great achievements.
Thank you.
Just while colleagues perhaps typing into the system, I wanted to ask, and I think it's great that you're mapping out the future years of the PhD, and you're certainly off to a great start. And I think you mentioned, is it Southern Launch is the industry partner you're working with?
Yeah.
When you get to the end and you'll have your thesis and your publications, what do you think would benefit Southern Launch and other industry partners? What would be the outcome of guidance that you would summarise, perhaps not in the thesis, but another form of publication that would summarise your findings to allow them to pick that up and implement that in their own business? Do you have a thought on that?
Yeah, I have a thought of that, and I think that will be part of my potential impact of, the very last thing that I will have when I'm done with my project, which is having a intelligent security control to detect cyber attacks in a space system, and also the integration of software-defined networking in space system, just so space systems can leverage all these benefits that SDN brings to a network.
Excellent. I think the vision of the path to adoption of the research outcomes, the work that you're doing into the PhD is critically important and part of the role of SmartSat in supporting, communicating. So that sounds great.
Yeah.
Just see whether we've got anything there. I don't think we've got any other questions at this time. Wakomba, look, thank you very much for your presentation. Excellent progress to date.
Thank you.
We've got one here from Peter Kerr. Peter, you need to be quicker on the typing. We must get you in contact with Lewis at DST Group about SDN work. And do you know Shane?
Yeah, he's my industry supervisor.
Great. We might try and follow up with that to provide some support. Yeah. So see whether we can link up, and again, supporting that path to adoption of your research. Fantastic. Look, thank you very much for your presentation today. Really interesting work.
Thank you. Thank you, everyone.
So stepping into our fourth presenter today, and Sam Hilton is a PhD candidate with RMIT University. He has taken on the challenging problem of how space operations can be transformed from a slow, perhaps manual tasking of single satellite operations into a largely autonomous distributed system that enables dynamic planning and tasking. Sam has a Bachelor of Science and Master in Engineering from RMIT, and he's continuing what is, I'm sure, great work with the RMIT. Sam is also another one who's dabbling in a little bit of work at the moment, and very much closely aligned to a number of industry partners. So Sam, if you are with us, welcome you to give your presentation.
Hello, thank you. I'll say hello on the camera once, but my internet is a bit shoddy, so I'm just gonna show that I'm a real person, and then I'm gonna flick it off. Yeah, thanks for the introduction. Yeah, let me share my presentation and my PhD journey so far. So the title of my my project is Human Autonomy Teaming for Intelligent Distributed Satellite Operations. So yeah, as it's correctly mentioned before, I'm really looking at how the space and the ground segment must evolved with this effectively increasing sort of autonomy in space systems. My supervisors are Rob Sabatini and Alex Gardy and Graham Dorrington from RMIT University, who are actually also now at Khalifa University in the UAE. When I started this project, it was through Northrop Grumman, so they were the industry supervisors, and that was Dr. Nita Azur. She currently doesn't work in that area anymore, so but you know, I'm at the end now, and she helped me really sort of you know, scope and formulate my project. So I'm very thankful for that. As was also correctly mentioned, I'm currently in the industry as well. I work at a software company in Melbourne called PHM Technology, which develops software, which is pretty relevant for my project, and is now sort of incorporated into the end of it. And I will discuss how that is. So just a little bit of a research background. I'm sure everyone here, the audience, is pretty familiar with what sort of distributed satellite systems are, and you know why there is a shift towards them. And it's really so we can do, you know, perform sort of missions at scale, right, with the smaller non-monolithic platforms that sort of effectively work together and provide what I have down here, a more responsive and resilient sort of option to addressing, you know, the growing needs of both the sort of scientific community and also the defense industry. So these obviously come in a number of different forms, you know, from constellations, swarms, clusters, fractionated trains. But yeah, so I mean, where I started is like, how do we kind of actually achieve this responsive and resilient capability using DSS, right? And fundamentally, it comes down to moving from what is a sort of a deliberative sort of approach, right, where satellites might have individually sort of pre-planned tasking, right, to more of a sort of reactive type thing. So they react to their environment. It's more based on you know, what they see in front of them rather than what is predicted in the future, right? And it's kind of you know, a well-known I guess a level of autonomy. This one's provided by ESA, but I think NASA has something similar. And what we're trying to do is really get from, you know, these lower levels of E1, E2 up to E4. Of course, there is a number of challenges and implications on this evolution, right? And that's what I'm doing my PhD on. So what are these? So two kind of things that I've focused in on the actual system autonomy that is required, right? The key functions of system autonomy, right? And then the change in the operations based on those autonomy. So there's a number of things, you know, of autonomy that we're, you know, in spacecraft that is being actively researched and implemented and tested. But some of the key core functions that allow that mission capability are of course, the scheduling sort of problem. So what task do I do next? Our trajectory related things. So, you know, we have to be able to optimally reorientate a satellite. And of course, other types of things like how do we deal with reparations, so malfunctions, so on. They're not directly the focus of my PhD, but I do consider them. Of course, if we're shifting the autonomy from, well, if we're shifting the functionality that was typically performed or historically performed at the ground station to the space level, we also have this kind of new sort of operational paradigm, right? Important thing is that if you make something more autonomous, then the human role disappears. It's not quite true. What it actually does is it just changes, right? Becomes more of a supervisory role, right? And so the question is, well, how do we sort of transition to this and manage this? And that forms the other sort of the part of my PhD. Of course, you know, they are more sort of a, I guess, higher level, you know, I guess, perspectives on the problem. But when we start to think about, okay, well, what is the capability, as in the mission that we want to, well, what is the capability and for what mission do we want to perform? Can we start to kind of analyze the problem in a little bit more detail? I've chosen to look at the sort of a space-based surveillance capability. So effectively distributed tasking of satellites. You can sort of see here with a simplified 2 sort of satellites to monitor RSOs, right? So resonant space objects, we all know that, why that's important, Kessler syndrome, so on, the sustainability of space, right? Why do we do that? Okay, well, it's for a number of different reasons. Mainly is that we want to be able to launch things into space safely, and that we also, when we are in space, we want to know when we want to maneuver, right? The mission that I've focused on, which was a sort of a large focus of my research group at RMIT, is multi-domain traffic management. So it's towards how do we sort of start to integrate air and space traffic management into this system, right? So we're thinking about effectively how this leads up to the safety case, right? So we have, you know, here's an example profile of something like this. So how can these space-based surveillance capabilities support missions such as this, right? So kind of looking at my research scope, basically I've been looking at the actual design of the platform autonomy, so the planning, the optimal trajectory related things, sensor models for the observation of RSOs. Been looking about how we quantify that uncertainty and how we propagate that into the future. But really what it's come down to is when we integrate this distributed autonomy, you know, at a systems to systems level, how do we start to build the safety and the mission assurance case for that? We know that we can't look at these platforms individually and look at reliability and the functional safety of these things individually, because they don't perform their function individually. They do it at a much larger scale. So what I've been doing is basically developing these surrounding aspects and now pulling them into a centralized sort of perspective. Primarily using what we called a model-based methodology, right? That comes back into the company that I'm working for now. PHM develops a model-based engineering software, right? Which is targeted at effectively quantifying the risk in systems of systems sort of architectures, right? So I'll get to describe that a little bit more detail when I get to it. So a couple of key sort of research questions here. I won't read them out to you, but two main areas: the actual autonomy, right? So the mission planning, the trajectory, and so on, and then the safety mission assurance case of these types of these systems, right? How can I look at it? Developing effectively a framework, translatable framework that can allow people to assess these things sort of rapidly, right? And the way you do that is you use model-based systems engineering approach, which allows these rapid sort of trade studies to model these interactions and start to understand the risk in your system. So when I talk about risk, I'm thinking about the effect of hardware and software functionality, as well as cyber-related threats as well, is also a key part of it. Okay, I'll go through a couple of the research highlights over the course of my PhD. The first thing I really looked at is that I know that what this mission all comes down to is we're looking at the collision avoidance maneuvers, right? And to do that, we basically have to understand where a resonant space object will be at a point in time, right? Or understand the expected range of where that will be, right? And that's really where we start to look at the uncertainty in its position. So I've looked at that from a couple of different angles. The key one is really starting to understand, well, how valid are those assumptions based on certain types of measurements? So both the geometry of radar and the performance of radar systems, as well as optical systems. Based on that, how long are these measurements useful for? So how far can we propagate these into the future while they still hold their sort of statistical, meaning, right? So, how long do they, in most cases, hold the assumption of normality, right? So that was the first kind of part. The next part was moving on to looking at, okay, well, we know how to quantify and propagate the uncertainty. How about, we have the platform, we need to know the autonomy aspect of reorienting the spacecraft, right? So both in terms of attitude and in terms of orbital maneuvers, right? So looked at and implemented some meta-heuristic methods, optimization methods to do that. Why we do that is that basically they're not affected by local sort of convergence, right? You don't require too much human input to sort of guide the problem. They might not necessarily converge to the globally optimal solution, but they will always get to an optimal solution. So that allows them to be very adaptive and be performed on board. So that was the sort of the reasoning behind that. So this, allows us to think about, the key, aspects in terms of when I think about the larger safety case, the software functionality, the dependencies on data, and this sort of thing, and how that basically rolls up into a bigger system. The other part of it, which I highlighted, is the distributed mission planning aspect, right? This is another sort of key area that's focused in autonomy for spacecraft, and it's that we need these kind of things to act as a group, right, and towards a combined mission goal. But we need to basically, for that to happen at large scale, we need to, in a lot of cases, reduce the reliance on communication links, right? So a lot of this is that we can't rely on sharing of information through key inter-satellite links, and those assumptions are are a bit off when you start thinking about, well, I have to reorient the satellite as well as maintain the communication links. So the idea is that we can use bio-inspired methods to sort of coordinate these space assets. And at this time, I was looking at effectively a distributed sensor tasking problem. And it's effectively like a multi-agent coordination mechanism where, given broadcasted information from a ground station, we can start to basically coordinate the tasking of these satellites, given a common goal, which is sort of represented there as the objective function. So we're looking at, in this case, reducing, duplicate tasks, but increasing, making sure that the satellite looks at tasks that have a higher probability detection for them, and ones that also have a more like a higher track weighting, so more importance to look at. You can sort of see the effect of this basically global sort of iteration of the satellites, starting off with a high satellite utility. So they're kind of thinking about themselves, but as the information is sort of shared through this bio-inspired mechanism, which has low reliance on inter-satellite links, the mean satellite utility drops down, but the global utility goes up. So we're looking at we're basically working together. Satellites are working together to share to meet their mission goal. So the next part, which I touched on briefly, was the how do we now known this types of autonomy, right, and the software and the algorithms, how do we put this together and represent understand and start to build the safety and the mission assurance case of this in a kind of a framework which is repeatable and people can sort of pick up and use. And the way they've done that is by using and adopting this model-based systems engineering methodology through a tool that Australian tool that is made by PHM Technology, where I work, called MADE. It's a tool it's used widely, mainly by US sort of defense agencies, but also we have a close relationship with NASA Goddard. So the idea is that we can represent these platforms, the interaction between them, and start to understand, how and where these how these systems act in the presence of failure, right? And how can we build a safety case for this? So this is just a little bit more detail about the tool here. So as I said, the tool allows you to basically provide you a number of different perspectives, both functional, as also reliability perspectives. And you can start to understand, given hardware and software failure modes, how this might propagate, how they propagate through the system, right? And where you might need to put control measures to effectively to stop this propagation. This helps in the support of, a lot of key safety and mission assurance analysis, such as, functional related things, fault trees, all those different types of flavors there. What you're looking at here is actually a model built in conjunction with self and Goddard Space Flight Center of a SmartSat platform, which I've started to use for the basis of these analysis, right? This is a freely available model, so if you're interested and you want to use it for this type of analysis, please get in touch and we can sort that out for you. In any case, my job has really been about taking this model and effectively scaling it up to the mission level, right? And understanding, well, when we have a number of these platforms here, how does this distributed sort of autonomy start to interact, right? And how can we do these types of analysis at a systems level, right? And I do this by looking at a number of different perspectives that the model provides. So the sort of mission reliability and availability, as well as the functional perspectives. And these all form and relate back to key analysis prescribed both in, the defense standard sort of domain. So MIL standard 882E is one of them, as well as sort of the NASA standards as well. So this is something that, that people are starting to, satellite providers are starting to have to provide, right? These estimates on reliability and availability of missions, where the functional piece starts to look at, well, how can I incorporate, certain behavior and routines to demonstrate sort of fail-safe properties and of the system. So I was recently at the SmartSat satellite conference in Utah a couple of weeks ago, and was looking at this perspective here, the mission level reliability and availability. And yeah, presented that there. Go into too much detail, but basically looking at, given a representative architecture of this surveillance mission, some high-level requirements based off the standards, how we can start to model this, the reliability, not just at the platform level, but also the required functional configurations of the satellites in their respective planes, and how we can build that up to start to get reliability numbers at a mission level. So that's where I'm at. The current bits, or the final bits, my project is now I'm looking at the sort of functional perspective to do more of those functionally orientated safety and mission assurance analysis. So there's some publications to date, probably updated. Yeah, slightly out of date, but yeah, you get the idea. So yeah, any questions? Thank you.
That's great. Thanks, Sam. It's really interesting work and probably more complex than I can actually comprehend. But I've actually got two questions. One is quite simple, and perhaps shows my lack of understanding. But when you're driving down the road and you come to an intersection, general rule of thumb is you give way to your right. So in a spacecraft, who's responsible for giving way? That's my first question. My second question is, you talked about the modelling that you're doing and the ability to have decision making and future prediction and extending that future prediction out. I'm interested in, what do you think is the optimal time frame for these predictions, particularly given that there'll be lots of groups as more satellites go up and they're all manoeuvring and changing their orbits or adjusting. Is it about predicting long into the future, or being able to make the decisions quickly, taking in to all of the variables? Interested in your perspective on that one.
Yeah. Okay. Well, I'll answer the second question first. Well, I'll attempt to answer the second question. Yeah, I think it's. I mean, it goes back to the methods that you can apply to propagating that position and velocity estimates in the future, right? It gets, obviously, the longer you do this, the more nonlinear and your mathematical assumptions start to break down like pretty heavily. So then you start to rely on more sort of complex methods, right? So there's that aspect of it. I mean, the ideal would be that you could predict everything in the future, but then of course you have to then take into account the possibility of maneuvers between that an initial prediction point and your final. So it is I'm not sure I have an exact question, an answer for that. I mean, there's obviously a balance there, I think, right? The idea is that if we can have the onboard satellite capability to perform those maneuvers in enough time, I think that's really probably the ultimate goal. So yeah, I think that's hopefully I've answered a bit of your question there for your second one. The first question was again about who should move, right? Yep. Well, maybe that's a question for the space law person, but I think I mean, who should move, right? It's hard. I don't know. I think, there's usually, from my understanding, there's the way that this works. There's a lot of times these people get in contact with each other. Sometimes they get a conjunction data message between the two, respective, hopefully only two, operational spacecraft in this case, so cooperative sort of scenario. Usually something through like an email, and then they go from there and sort of let's say come to some sort of resolution. So I don't know if there's an answer.
No rule of thumb.
No rule of thumb.
That's all right.
It becomes even more complex if you do something like shoot a laser at a from the ground, which we're doing, at something in space, and it's not your object, but you've now moved it, and so you were the last to touch it, and then it's found out that is going to hit something. Is it now your fault? I mean, it's pretty difficult.
An interesting area.
An interesting area for sure.
Yeah, and Peter again is the risk due to ambiguity of moving satellites, perhaps not out of risk, but into danger. Yeah. Got a question from Richard, who is one of our chairs with UniSA. He's talking here about there are many definitions of autonomy, but do you have clarity, or can you provide clarity in relation to your definition? between model-based and goal-based approaches in your research?
So I think, yeah, there are a number of different scales. I mean, what I'm going off is primarily the ESA table here. I think the autonomy level that I'm really looking at, I guess, is probably at really on the larger, like on the larger end, right? Where I'm thinking about not necessarily any interaction straight away for between the human and the spacecraft. So, they will perform the tasking by themselves, given the information that they have. So, I mean, I've kind of, I'm not, looking at the discrete levels so much. Of course, I think it really comes down to how much, obviously, the interaction you have with the human, which goes into the, human factors related research and all that kind of stuff. Yes, I have seen these scales, but it's not something that I'm directly thinking about, I guess.
That's all right, Richard. We can always pop you and Sam in contact and share some contact information, because you're certainly interested in the links with Scarlet Alpha.
Yeah.
Look, Sam, thank you very much for your time and presentation. Really interesting work that you're doing. That was great.
Appreciate it. Thank you.
So, colleagues, that concludes at least the first part of our series of presentations today from our 4 PhD candidates, and it always amazes me the depth and breadth of the work that the cohort is doing. But transitioning now into, I guess, a keynote speaker today, and I'd very much like to welcome Professor Craig Smith, who is the SmartSat Mike Miller Professorial Chair in Telecommunications with UniSA. Craig took up this role just earlier this year. It's fair to say during his career, Craig has done many things, from research scientist and university lecturer right up to corporate executive, CEO and chief technical officer across multiple space and defence disciplines. In a career spanning over 35 years across those defence in space and defence industries, Craig's most recent appointment was the Chief Technology Officer with Electro-Optic Systems, or EOS, and we've been very pleased to have Craig engaged with us across the life of SmartSat, and particularly around our Chorus project, which has been a fantastic program of work that we've had. Craig today is going to share some of his experience and perspectives on the research and industry interactions, and no doubt about building relationships and managing expectations. Craig, thank you very much for your time today. Very much looking forward to your talk.
Thanks, Andrew. Today I'm going to share a little bit of my experience, both from being working as a university researcher, working in industry with universities, and now working in universities with industry again. So it's been an interesting path. So that come up all right?
Yeah, we've got that.
So I just wanted to, so I'm going to go through a bit of a video resume, perhaps, is just talking about some of the things I've done, the things I've learned along the way, and how it relates to working with industry, in industry, and doing things of value. So I started off at the University of Melbourne. I did a bachelor's degree in physics, and then a PhD in physics and astronomy. And just a few highlights there. So the PhD was actually about looking for black holes at the center of our galaxy. Primarily, it was a lot of building infrared instrumentation. I think I had one of, if not the first, thermal infrared camera in Australia. And this was back in the days when just to detect the chip in that camera was $100,000 in the days when $100,000 actually was serious money. What I learned in that process was at the university, there's, I'm sure you're all familiar, there's resources are limited. And so along the way, I had to sort of learn a whole lot of disciplines. Primarily as physics, start off in physics and chemistry of the interstellar medium. But then in the other aspects of instrument building, it was optics, mechanical design. We had a workshop, we'd make things, but you had to design it yourself. Electrical design, we had, again, workshops that would build stuff for you, but you had to tell them what it was, and develop the software. And this was back in 1984. We had one of the first PCs in the University of Melbourne. Before that, all our work was done using punch cards and paper tape. So it was a bit of a revelation. And the point about this is really showing the skills that you develop. One part of this is the skills you can develop doing a PhD and how that can set you up for later life. Along the way, I also spent 10 years in the Australian Army, where I was an infantry platoon sergeant. And the things I learned there, which was actually a pretty formative part of my life between the PhD and being in the military, first thing you learn is teamwork, working together. You learn leadership and management, and they are very different things. You learn discipline and hard work. And I would just, some of the hardest things you ever do are actually turn out to be the most memorable. And the things you talk about, even 40 years later, we still talk about things, the tough things we did. So you can never shy away from difficult things and adversity, because they can be the most rewarding. You learn friendship, mateship. It was a great thing. That's me on the left-hand side of that picture when we won a 3 military division, a military skills competition. And the other thing I learned was instruction and teaching. The Army's good at teaching skills. It's not quite the same as education, but it has a structure which has been learned over hundreds of years of how you instruct people. And my point about that is really that, at least at university, I had some absolutely lecturers who were no doubt good researchers, but were absolutely terrible lecturers. And we had some absolutely great lecturers, and invariably I found out that the great lecturers had some kind of training in teaching. And so anybody who looks at doing an academic career, I would also suggest that you get some kind of training in teaching skills. From there, back then, it was in the 80s. We were post-Vietnam, before 9/11, so there was nothing going on. The Australian Army seemed a bit directionless, so I left the Army and took up a ARC research fellowship position for 4 years, and then a senior research fellowship position. Again, working in infrared astronomy and instrumentation, but also had fantastic time with Antarctic IR astronomy as well. And that's me down there at the South Pole, where we spent a summer, again, learning independence, but also, you get some pictures of there working as a team, just 2 or 3 of us. At this time, though, that's me and a postdoc. So around this time, I realised that there's not a whole lot of resources that are being available, and I wanted to do things that were of significance. And science and engineering in those days weren't usually done by just one person and a student or a postdoc. I wanted to do bigger and more significant things. So I left the university system. Why won't the slide change? And took up a position as the head of research and develop at Electro-Optic Systems, which is a Canberra-based company. And at the time, that was mostly working in geodesy and satellite laser ranging. In satellite laser ranging, we were tracking cooperative satellites to about 1 millimeter accuracy in space, mainly for geodesy and satellite navigation. We would track GPS satellites, GLONASS satellites. So before GPS could tell us where we are, we had to tell them where they are. And geodetic was work with measuring the terrestrial reference frame. The WGS system is tied to celestial reference frame through satellite laser ranging. So I spent a year doing that, and then sorry, slides don't want to behave. And took up a position, or was appointed as the Chief Executive Officer of our US subsidiary company in Tucson, Arizona, where we were building large aperture telescopes and beam directors. Had a great time going around the world building major observatory systems. But one of the lessons I learned along the way was metrology, and the picture in the middle there shows one of the first Shack-Hartmann wavefront sensors that developed, and we use that to characterize the optics. And what you soon come to realize is that you can build anything that you can measure, and so metrology actually is critical. And these are just some of the experiments. The systems we built around the world: one in India, one in Hawaii. There's a couple there in Hawaii, and even one in Sky Mapper in Australia. This is another example. In 2003, there were bushfires came through Canberra. You can see on the picture on the left, that's the Mount Stromlo, where our observatory was located, in flames, and the two little pictures on the right show our telescope and observatory after the devastation of the fires. But that was January 2003. By October, we had rebuilt our tracking station, as you can see in the picture at the bottom, and really that was the testament of how much you can achieve. That was October, so 10 months after we'd started reconstruction, we had the system up and running again. And that's just a testament of how much you can achieve when you work together. After that, I had a bit of a change and moved to be the CEO of EOS Defence Systems, where we built remote control weapon stations. The top left picture shows the actual weapon station, which carries a 50 caliber machine gun, and we installed those on the Bushmaster protected mobility vehicles and the M1 Abrams tanks. And as a highlight actually of work I've done, seeing those systems in operation in Afghanistan. So there's two images on the right of our systems in operations and helping to protect people's lives, or our soldiers' lives. After 4 years there, I was back to Space Systems, working in space domain awareness and space control. And these are a couple of facilities. The left top is Mount Stromlo. The bottom left is the system we built at Learmonth in Western Australia. All things are laser track, building lasers and space domain awareness. And an interesting little picture there down the right, we built a 2.5 meter telescope in Thailand for the Thai national government. And this is the Princess of Thailand when we went to do the opening of the building. And all the public servants in Thailand get to have a fancy Navy-like uniform. So it was an interesting experience. One of the great achievements I felt was that we won as US Space Systems, won the Australian Defence Magazine Large Space Business of the Year 3 times in a row, which again, to me, it shows the value of teamwork, working together, and you can achieve some pretty great things. There's some images here of the systems we built and laser ranging, tracking things in space. Between 2012 2018, I wrote the Space Environment Research CRC proposal and led one of the research programs where we were looking at moving using photon pressure to remotely maneuver space debris. So this was a collaboration, a great collaboration between industry and universities. Included EOS, Lockheed Martin, Optus, ANU and RMIT and working together, and it was a pretty good program. And down the bottom there's a little optical phased array system that is a linkage program working with ANU. We built this optical phased array. So even in industry, I've been working with universities for a fair while. And more examples of images of lasers and satellite tracking and adaptive optics systems. In 2021, I became the CEO of Kiwi Star Optics in New Zealand, where we were manufacturing large optics, and spent a year there. And I was also the Chief Technology Officer, became the Chief Technology Officer at EOS, where a lot of my engagement was with, a lot of my work was engaging with universities and also scouring around universities, seeing what technologies were developing that may be valuable in the future. And then in the final last 3 years or so, I did a lot of work with the SmartSat CSC and the Chorus project, where we developed a hybrid optical RF terminal. I think it's been another great success of industry and university collaboration, where we all benefit from working together. And so earlier this year, I started with the University of South Australia and took up the SmartSat CSC chair in telecommunications. So this all comes back to, a lot of that comes back to this program, working telecommunications. Also, during the CERC program, working with the Japanese, we did an optical communications experiment with the Hayabusa satellite. We were able to establish an optical comms link at 2 million kilometers distance. And this program is somewhat different, 2 million kilometers, and in this one, but it's another example. It's an example of different technologies being applied in different ways. So that's kind of the run through of, and the point of all this is there's lots of interesting things you can do, fascinating and valuable things you can do in an industry career. And so the final, there's a couple more slides, but an academic career is not the objective of doing a PhD, and should all remember that only a small percentage of PhDs go on to academic posts. But that's not a failure, that's a success. Because for me, PhD is the training ground of tomorrow's technical leadership, and we need more of that leadership now than ever before. We have so many technical programs being developed in defence and other departments that we need to be training as many engineering, science, technology people as we can. But I would also say it's not just a curiosity or a job to do a PhD, but we have some sort of responsibility to give something back to the community and not just pay back your HECS fees. So my personal philosophy is to leave the world and the country a better and safer place than it found it. I think that's talked about. Yeah, and so I wanted to do things that were significant. So I had great 10 years working in a university doing curiosity-driven things, but then I really wanted to do something which was more national and international significance, and something that gives back to society. So that's why I left. But I'm trying to show that there are, I think, an infinite number of pathways in industry, defence, government, and even academia for technology and science trained people. I would say industry can be incredibly rewarding. You can do fantastic things, and you tend to get paid better than an academic career. All of that's the motivation for doing it, but it doesn't hurt. And as I said, I think with all the AUKUS and shipbuilding and major programs going on at the moment, we just need all the technical leadership and capability that we can possibly stitch together. So finally, working with industry, and I was going to say, it's pretty straightforward. It's all about relationships and trust. You have to form a relationship, and industry needs to, as an academic, you need to form that relationship with industry, and they have to trust you. I would say, if you're looking for working with industry, you need to be realistic. You need to be approachable and communicative, and it's not always something that comes easily to scientists or engineers. A lot of us, myself included, can find that uncomfortable, but it's just something you have to do. A key thing is to actually deliver what you say you will. Open-ended and lack of outcomes, just industry hates that. And as an industry partner, we're looking for some sort of return on investment. Industry is always looking for something, something to sell. So you have to be able to help them sell their product, or a better product, for them to be interested. Typically, industry takes a shorter-term view than academic timeframes. So you have to be aware. So telling you to deliver something in 5 years usually doesn't cut it. They're usually looking for something in a year or two. Yeah, and we need to be prepared to take systems to, as academics now, we need to take systems to a higher readiness level, or a TRL, than you might do just as a scientific experiment. I'd say, using blue tack and sticky tape doesn't cut it. You can't sell that to a customer. It's a proof of principle maybe, but you do have to be able to show that there's a pathway to taking things to a point of sale. I think I said it's all about relationship. Networking is essential. Even if it's hard work, places to go to meet people, to do the right thing. You've got to, sorry, I was going to say industry is busy. They're not going to come chasing you usually. You need to chase them. So you need to go to industry meetings and associations, Space Industry Association, SPIE is great. It's sort of an industry body, but there's lots of technical work where universities can contribute. Those trade shows at those SPI meetings are great places to go and meet industry. Talk to them. You have to communicate, find out what their issues are, where there's things that you can help, and then offer, provide that technical assistance. So the question is, I would say, is why do you want to work with industry? And certainly I've seen recently that there's a definitely shortage of research funds, and so everyone's looking for additional, and universities looking for additional support. And my experience has been that the government really wants more commercialization out of universities, and it will reward academic and industry collaborations much more than if you're on your own. If you working just as an academic position, a role, then you're kind of stuck with the ARC funding and the limited funds that brings. But with if you're working with industry, there's a much bigger pool of funding support that opens up. One of my comments and my bugbears, industry also has its own expertise, and academia is not the source of all knowledge, so we do need to be respectful. So I think finally, my experience, I'm a bit unusual. I started as a researcher for 10 years, 25 years in industry, now academic again. So it makes me a bit different, having worked on both sides. But for me, the benefits from industry of working with the universities is you get access to a wider range of expertise than I could possibly afford to develop in-house. Again, EOS is one of the larger space companies, but it's still an SME really. And the other thing, I got access to expertise as I needed it rather than keeping it on staff. So it was a cost-effective way of getting expertise. I got access to state-of-the-art equipment that I couldn't afford myself. For example, some of the state-of-the-art diamond turning and coating machines was a great benefit of working with the universities. And actually, I will say access to a wider range of knowledge and advice. So different perspectives coming from academic groups have always been valuable and help you avoid groupthink. And the other thing I found, I actually made a number of long-lasting friends through working with academia. So finally, we talked about the benefits of industry working with the universities. Some of the issues is lack of accountability. One thing we used to hate is we'd provide cash and the university spend it, but there was not really very much accountability about how that got spent. So in the end, it comes back to trust. I think I said before, comes back to trust and doing what you said you would do, and being prepared to accept timeframes and schedules, and not leaving things open-ended. So the other issue for industry working with the university is just knowing what's there. As I said, my role at EOS, a lot of it was to go and find capability that was valuable to the company, but as I said, industry tends to be busy, so you need to go to them, find them, and then help them out. So you can have a lot of misses in doing that. You might have to do a number of pitches before you find the right people to work with. But I think if you do as coming from the academic world, you'll actually reap a whole world of benefits, both in funding and interesting projects and projects that actually contribute back to society, community, and have national and international significance. So that's kind of me. I'm thoroughly enjoying being back in the university academic world, but I also thoroughly enjoyed my 5 years in industry. So I'll leave it there.
Fantastic, Craig. Thank you very much. Some great insights into that. And whilst we towards the end of the session, I'm keen to let colleagues have the opportunity, if they've got questions, pop them in the chat, or maybe even raise a hand. But Craig, you made a good point, and some things I was going to emphasise. Research can happen in industry. Even SmartSat's tapping into wonderful experience and capability in the industry. So as a research pathway, it can continue in industry. And you talked briefly about the need to go out and find industry, go to their events, go and meet them, build the networks. I was interested, just while questions are coming, what were some of the things that you did or stood out to you when you were looking to identify talent and capability? What were the sort of things that jumped out at you and said, right, I've got to go and meet that person or send them an email?
I always kept am I still on?
Yep.
Yeah. Yeah. I guess I used to always keep my ear close to the ground. And the work that we did at EOS, I lent itself to being involved and going and talking with university staff. But there was technologies that you wanted, so I would go out and visit universities. I would actually give presentations about what we do to find out, to try and draw out what people have and where they could assist. And it would, yeah. So does that answer the question?
I guess that's certainly one example whereby perhaps there's opportunities for our researchers network, and they all have their own seminars, but maybe invite an industry presentation to one of the local faculty or research lab seminars to be able to showcase and listen to what they're doing and showcase of what you're own doing. I guess it's about allowing yourself to be identified in amongst the pool of everyone else to try and get that attraction and future career opportunities.
Yes, absolutely. So it's putting yourself out there, but and it's, as I said, I think it's uncomfortable for a lot of people working in universities, but you just have to do it if you want to have that have those benefits.
Fantastic. Any questions from colleagues where they want to put up a hand and ask Craig directly? Okay, well, alrighty, as chair of the session, I'm going to take my second question, and perhaps the last one. Could you describe, or do you feel that you're jumping in and out of academic and industry? What was the value of that, particularly jumping out of the academic into industry for the next phase of your work? If you look at ARC research fellows, whether they be future fellows or early career research fellows, those that have spent some time in industry statistically do very well over those that don't. So really interested in your thoughts around spending a little bit of time with industry and then potentially coming back to academia.
Yeah, I think you learn a different set of skills, different perspective, more focus probably on outcomes, and access to a larger pool of resources and capability. As I think I talked about, doing things with one or two people is one thing, but then going to places where you have bigger teams and you're working with 50 people, it allows you to do things of more significance, and then you get exposed to all the different capabilities, technologies, disciplines, which you can also bring back to university or academic life when you come back.
Yeah, fantastic. Look, Craig, I think we'll call it there, mindful of time. Don't have any other questions in the chat, but I think there were some fantastic messages and perspectives that you've provided. Now, you're spending a bit of time at UniSA, but I'm sure you're accessible to many colleagues. I would encourage all of our students to... Can I just make one parting message? To me, it's all about teamwork. It's all about teamwork and working together. And together we can do a lot more than we can do by individually. So that is my objective. It's kind of part of my objective here at UniSA and SmartSat is to try and connect the dots and make people work together to be more than the sum of the parts. Fantastic. I think that's a great way to end today's session. So please let me pass on a vote of thanks to all our presenters today and extend a vote of thanks to everyone who's attended. Another great session today. We will be putting the recording on YouTube and make it available to on our intranet site. I believe our next session is planned as part of our SmartSat conference scheduled for 12th and 13th of September. And I know many have already registered and looking to attend. So we're very much looking forward to seeing everyone at the conference. And please, those people who extended opportunities to catch up and reach out and share information, that's really a foundation piece of why we run these events. So make sure you do reach out and catch up. Look, thanks again to everyone. We'll conclude our session there and thanks again for everyone's attendance. Bye for now.